This is CIE March 2021 Probability and Statistics Paper 1. Okay, question 1. We have a fair spinner with 5 sides, and we want to find the probability that a score of 3 is obtained for the first time on the 8th spin. Okay, so given that we're looking for one success and we're trying to find the first time it occurs, this sounds like it is a geometric distribution. So the spinner is distributed geometrically, and we want the probability of success. So we'll take scoring a 3 to be our success, and the probability of scoring a 3 is a fifth, or 0.2. Okay, let's just have a quick look at our geometric distribution. So the probability that it happens on the 8th go, I'll write up that formula out actually. It says PR equals P brackets 1 minus P to the power of R minus 1. Now, that's a complicated way of saying, well, if it happens for the first time on the 8th spin, that means on the 8th spin the probability is 0.2, but on the previous 8 spins we have not scored a 3, so that's 0.8 to the power of 7. So those are the 7 spins where we haven't got a 3, and there's where we have got a 3. So I'm going to put that into our calculator, 0.2 times 0.8 to the power of 7, and we get 0.0419. So 3 significant figures. So in question B, we're asked to find the probability that fewer than 6 spins are required to obtain a score of 3 for the first time. If that's fewer than 6 spins, that means within the first 5. Okay, so probability of a success in the first 5. Okay, now one way to do that would be to work out P of x equals 1, add P of x equals 2, add P of x equals 3, etc., etc., using the same formula as we used above. So for instance, for P is equal to 1, it would be 0.2, and then plus 0.2 times 0.8, and then plus 0.2 times 0.8 squared, etc. But there's actually a much quicker way of doing it. Instead, let's work out the probability of the opposite situation. So the probability of failure all of the first 5 spins. Okay, well, the probability of failing for all of those first 5 spins is 0.8 to the power of 5. Okay, now if we didn't fail in all of those first 5 spins, that means that we've had a success in one of those times. So the probability of success in first 5 is simply 1 minus 0.8 to the power of 5. So let's do that. 1 minus 0.8 to the power of 5. 0.672 to 3 significant figures. Question 2. This initially looks like it might be one we could do using a probability tree. Each day she wears exactly one of these scarves. So I'm going to start my probability tree here. And we have red, blue and yellow. And we have the probability 0.2, 0.45 and 0.35. When she wears a red scarf, she always wears a hat. Okay, so that is hat with a probability of 1. When she wears a blue scarf, she wears a hat with probability 0.6. So we'll have hat and no hat. So So when she wears a blue scarf, she wears a hat with a probability 0.4, so 0.4 and 0.6. And when she wears a yellow scarf, she wears a hat with probability 0.3, so 0.3 and 0.7. Find the probability that on a randomly chosen day, Georgie wears a hat. So we have three routes along our tree diagram, 0.2 times 0.1. Sorry, 0.2 times 1, not 0.1, so 0.2. We have 0.45 times 0.4. So 0.18. And we have 0.35 times 0.3. So 0.105. And then we're going to add these up, so we multiply along the branches, add between them, so 0.38, 0.48, so 0.485. Part B is a conditional probability question, and we want to find the probability that Georgie wears a yellow scarf, given she does not wear a hat. So I'm going to set up my formula for this, and I always like to start with the other side of it. So y intersection not h is equal to the probability of not h multiplied by the probability of y given not h. And the reason I always like to start with this on the left hand side is it means whichever one has come first here for, so here I've put h, not h first, that means that the other one comes first here. So if I ended up with y here, then I would have not h and then the line and then y. And now I'm going to rearrange this so I get p of y given not h is equal to the p of y intersection h divided by p of not h. Okay, so I need to work out both of these things. So the probability of not wearing a hat, well, we have two possible routes for that. I'm going to work them out in red up here on the diagram. So the probability of not wearing a hat here, 0.45 times 0.6. Which is 0.27. And we also have not wearing a hat here, 0.35 times by 0.7. Oops, 0.35 times 0.7. Which is 0.245. So the probability of not wearing a hat is both of those things added together. So 0.245 add 0.27. Which is 0.515. And the probability of yellow and not wearing a hat is this one here, yellow and not hat, 0.245. So we're going to do 0.245 divided by 0.515. And we get 0.476 to three significant figures. Question 3 looks like a fairly standard normal distribution question. So the time spent by shoppers is distributed normally with mean 96 and standard deviation 18. Find the probability that a shopper spends between 85 and 100 minutes in the shopping centre. So let's first of all normalise our variable. So 85 subtract 96 divided by 18 is less than z, and 100 minus 96 divided by 18, this is what we're looking for. So 85 subtract 96 divided by 18, and we get minus 0.611. And 100 take away 96, which is 4 divided by 18, which is 0.222. Okay, so if I draw a quick sketch of my normal distribution curve, I want where it's between 0.222 and greater than negative 0.611. Okay, so what I'm going to have to do for this, the less than 0.222 is quite easy. Let's read that off our table. So 2, 2, 2, so this, add on that 8, so 0.5879. A little bit trickier for this one, to find the probability that z is less than negative 0.611, because then what I want to do is, so this 0.5879 is everything from 0.222 backwards, so then I want to subtract this bit on the left hand side of minus 0.611. So that is going to be equal to, now because I don't have negative values in my table, let me just do a quick sketch. Instead I'm going to look up 0.611. When I look that up, that's going to tell me what's on the left hand side, and I want what's on the right hand side. So I'm going to do 1 minus the probability of 0.611. So let's look that up on the table, 0.611. .611 is there and there, so 0.7294. So 1 minus 0.7294, which is 0.2706. And then I'm going to do 0.5879 subtract 0.2706, and that's going to give me my final answer. .317 to 3SF. Part B, again a fairly standard question. 88% of shoppers spend more than 2 minutes in the shopping centre. So the probability that t is greater than whatever this is equal to 0.88. We can normalise straight away or after, it doesn't matter. Z is greater than t subtract the mean, 96, divided by the standard deviation, 18, is equal to 0.88. So what this looks like on our normal distribution curve, we're looking for somewhere where on the right hand side of that point we have 0.88. Now bearing in mind to the right hand side of the mean here, that's equal to 0.5. That means that our line is going to be somewhere here with this area equal to 0.88. Now negative values do not appear on our graph. So instead what we're going to have to do is we're going to have to find the equivalent positive value, which looks something like that. And then we're going to make that value negative. So let's go ahead and do that and look up where the area is equal to 0.88. So this time I'm looking inside the table because I have the area this time. So 0.8, now we're close here, 0.8790. So ideally I'm looking to add on 10. There we go. So this one and this one gives me exactly 0.88. So we have 1.175. 1.175. So that must be at minus 1.175. So that means that t minus 96 divided by 18 is equal to minus 1.175. So we're going to multiply both sides by 18 and then add on 96. And hope it gives us a reasonable answer. Minus 1.175 multiplied by 18 and then add 96 and we get 74.85. Let's just have a look at the question and see if it seems reasonable. Well, given that our mean is 96 and 88% of shoppers should spend more than this time in the mall, that seems perfectly reasonable. I might just round it to 3 significant figures. 74.9 to 3SF. Question 4 is a discrete random variable question, and we're asked to draw up the probability distribution table. So we have x, which can take the values 1, 2, 3 or 4. And then we have the probability that x equals x. Now for 1, that means k times x, so k times by 5 take away x, so k times 4. So I can write that as 4k. When x is equal to 2, we have 2k times by 3, so 6k. When x is equal to 3, 3x times 2, so 6k as well. And when x is equal to 4, we have 4k times by 1, so 4k. Now we could actually work out what these values are, but at the moment it only asks us for it in terms of k. I guess it's in this next question where we may be going to use the fact that all of these add up to 1. Okay, so now we need to show that the variance of x is 1.05. Let's grab the couple of formulas that are going to be useful to us, and they are these two here. The expectation is the sum of xp and the variance is equal to the sum of x squared p minus the expectation squared. Okay, now I feel like it's going to be helpful to use the fact that all of these must add up to 1. So that's what we're going to do first. I'm going to add all of these up, so 4k plus 6k plus 6k plus 4k must equal to 1, so 20k equals 1, So k is 1 divided by 20, so 0.05. So I can actually make this table a little bit better, because now 4 times 0.05 is 0.2, 6 times 0, so this is 0.3, 0.3, and 0.2. So now I can actually use numbers in my calculations. So let's work out our expectation first. So E of x is equal to 1 times 0.2 plus 2 times 0.3 plus 3 times 0.3 plus 4 times 0.2. 0.2 plus 0.6 plus 0.9 plus 0.8. So 1, 1.9, 2.5 is our expectation. Now let's work out our variance. So the sum of x squared p. So 1 squared times 0.2 plus 2 squared times 0.3 plus 3 squared times 0.3 plus 4 squared times 0.2, and then we're going to subtract 2.5 squared. So that is equal to 1 times 0.2, 0.2, plus 4 times 0.3, which is 1.2, plus 9 times 0.3, which is 2.7, and 16 times 0.2, which is 3.2. Subtract 2.5 squared. So we have 1.4, 1.6, 4.6, 6.6, 7.3, subtract 2.5 squared, and let's use our calculator for that. 7.3 subtract 2.5 squared, and we get 1.05. Let's just double check that's what we were asked to find. Yes, which is what it is. QED. Question 5 wants us to draw a cumulative frequency graph. It is worth noting that these do not overlap, so we're going to need to use 4.5 here as our upper class boundary. So for this, I'm going to use a slightly different software. And we want, well, first of all, let's work out our cumulative frequency, because we're only given our frequency. So that's the first thing to notice. So our cumulative frequency is 12, add 16, 28, add 32, 60, add 66, 126, 146, 150, which sure enough adds up to what we were told it should. So we want this to go up to 150, 10, 20, 30, 40, 50. So it looks like we may, what should we do? 60, 80, 100. It's a slightly awkward scale that they've given us here. If we use the very edge of the paper, which I don't always really like doing, we can just about make it work. So let's make that stand out a little bit. And here we want this to go up to 60, 10, 20, 30, 40, 50, 60, okay. Right, let's make that stand out a bit first. Okay, so we are going to go up in 20s for our cumulative frequency. 60. 80, 100, 120, 140, and we can just fit on 150 there. Remember to label your axes, cumulative frequency, and then the distance, we're going to go up in tens. Again, remember to label, I think it's distance in kilometres, but let's just double check that. Yeah. And now let's plot our points. So at 4.5 we're going to plot a frequency of 12. So that is there. At 10.5 we're going to plot 28. At 20.5 we're going to plot 60. At 30.5, 126. So 30.5, 126. And at 40.5, 146. And at 60.5, 150. And then we're going to connect these up with straight lines. Remember, you can use, if it says a cumulative frequency graph, you can use straight lines or curves, it's your choice. And it's always a little bit safer to stick with lines because it leaves less room for error. And there we go, there's our cumulative frequency graph. Okay, you'll notice I've started from 0 and not negative 0.5 because we can't have a negative distance here in the context of the question. Now, we're told for 30% of the journeys, the distance travelled is d kilometres or more. So for 30% of the journeys. So what we're going to do is, first of all, we're going to find 30% of the journeys. So we have 150 journeys. So we want 30% of 150, which is 45. Okay, so that means for 45 journeys, the distance is d kilometres or more. So it's the top 45 journeys. Okay, so I'm going to go to my graph and I'm going to find the top 45 journeys. So here's 150. So essentially I'm doing 150 take away 45. And I'm finding the 105th journey. Okay, so the 105th journey, that's barely visible, let's try that again. The 105th journey is about here. So now I want to go down from this point, and I've got something like, so 25, 26, 27, and I think I'm slightly too far to the left here, so I think mine should be 27.5. So I think the distance is 27.5 kilometres. Part C is a relatively straightforward estimate of the mean question. So we're going to go to our table, and first of all we're going to need our midpoints. Let's write down the formula we're going to use first. our mean is the sum of fx divided by the sum of f. So x is the midpoint. So here for the midpoint, well, my class boundaries are 0 to 4.5. So I'm going to do 0 plus 4.5 and divide that by 2. And that gives me my midpoint of 2.25. Let's write in the other class boundaries very quickly. Now for all of these remaining class boundaries, it doesn't matter if I use these and do 4.5 add 10.5 and divide by 2. That's the same as doing 5 add 10 divided by 2. The only exception is this one, because the lower class boundary here is not negative 0.5, because we can't have a negative distance. So this is the only one that's going to end up being to 2 decimal places. So one to watch out for there. For the rest of these, either 4.5 add 10.5 divided by 2 or 5 add 10 divided by 2. Either way, you get 7.5 here. The next one, 31 divided by 2, 15.5. 51 divided by 2, 25.5. 71 divided by 2, 35.5. Watch out, they like to get you into a bit of a pattern and then change it for the last one. This is 101 divided by 2 is 50.5. So we're going to use our frequencies, not our cumulative frequencies, but our frequencies with our formula, with our x's and in our formula now. So we're doing 12 times 2.25 plus 16 times 7.5 plus 32 times 15.5 plus 66 times 25.5 plus 20 times 35.5, I'm going to run out of space here, and then plus 4 times 50.5, I'm going to cheat a little bit, and this is all divided by 150. Let's move that up a little bit. All divided by 150. Okay. So on the top I get 3,238. Let's divide that by 150. 21.6 to 3SF. It's always worth double checking you've typed these in correctly in your calculator. It's easy to make a little mistake. Here I'm feeling reasonably confident because 21.6 seems kind of reasonable when looking at the types of numbers we've got here for our distances. Okay, so I'm quite happy with my answer of 21.6. Question 6a wants us to find the total number of different arrangements of the 11 letters in the word caterpillar. I always like to rewrite these words with the kind of letters together. So we have a C, then we have 2 A's, so CAA, 1 T, 1 E, 2 R's, 1 P, and I, and 2 L's. Now let's just check we've got the right number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I always like to do that because then you can see the groupings of letters more easily. Okay, so if all of these were distinct and different, we would have 11 factorial ways to arrange them. But we have 2 A's, so we're dividing by 2 factorial, 2 R's, another 2 factorial, and 2 L's. So we're doing 11 factorial divided by 2 times 2 times 2. So 11 factorial divided by 2 factorial times 2 factorial times 2 factorial. I am aware that is just equal to 2, but never mind. Right. 4,989,600 sounds like a very big number. 4,989,600. Part B wants us to find the number of different arrangements where there is an R at the beginning and R at the end, and when the two A's are not together. So when you've got two objects that are not together, we consider that in a slightly different way. So first of all, I'm going to forget about the A's and I'm going to place the R's and think about the rest of the letters. So without the A's we have 9 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have an R at the start and an R at the end. Now, forgetting about the A's, the remaining letters we have 1, 2, 3, 4, 5, 6, 7. So without any restrictions, that will be 7 factorial ways. We're not considering the A's, we're not considering the R's, they're at the start and the finish. The only repeats we have are the two L's, so we have 7 factorial divided by 2 factorial. That's for everything apart from the A's. Because the R's are fixed in place, we don't need to worry too much about them. They just occupy those 2 spaces. There's nothing we can do. If they were 2 different letters, we'd have to consider the different ways around in which they could be, but they're not. Now we are told that the R is at the beginning and the R is at the end, so let's look at the spaces in which the A could go, or the A's could go. They could go there, there, there. So we are trying to put the A's into each of these spaces. So 1, 2, 3, 4, 5, 6, 7, 8 spaces we have for them. And I'm going to choose 2 of those spaces. Okay, the reason I'm using C and not P is because these 2 A's are identical. You could just as easily do 8P2, but that takes into account those permutations, so then you'd have to divide by 2 factorial, which is exactly the same as doing 8 choose 2. So let's plug that into our calculator. 7 factorial divided by 2 factorial. Divided by 2 factorial. And then times that by 8 choose 2, which is 70,560. Part C is a slightly tricky version of quite a common version of these permutations and combinations questions. Because we've got a selection of only 6 letters, we can actually start to consider the individual possibilities. So, with our number of R's, our number of A's, our number of L's, and any other letters. Okay, let's just highlight which the other letters are, just to make it a little bit simpler. We have a C, we have a T, we have an E, we have a P, and we have an I. So 1, 2, 3, 4, 5 others. So we've got 2 R's, 2 A's, 2 L's, and 5 others. Now we're going to write down all of our possible combinations of these. So we always need to have 2 R's. We'll start with maybe 1A and 1L, at least 1A and at least 1L. That would be 4 letters so far, so we'd need 2 others. Okay, 2 R's, 2 A's and 1L would mean we'd need 1 other. 2 R's, 1A and 2 L's would also be 1 other, and we could also have 2, 2 and 2. 2 R's, 2 A's, 2 L's and no others. Now you might be tempted to start doing something like this and writing 2 choose 2 times 2 choose 1 times 2 choose 1 times 5 choose 2. And that seems okay at first, except this is where this question is slightly trickier compared to other similar questions. We're picking 2 R's from 2, so this 2 choose 2 is fine. But here, when we are picking 1A from the 2, these A's are identical, so whichever one we pick, it doesn't make any difference to the selection of letters we've got. We would have 2 R's, 1A, 1L, and then 2 other letters, whichever A we took, and same with whichever L we took. Okay, it's not like this A is different from this A, or this L is different from this L, and that's how it differs from similar questions to this. So, we don't want this 2 choose 1, because they're identical. We don't want this choose 1 either, because they're identical. So in this instance, we are filling 4 of the spaces with 2 R's, an A and an L. And then we are just interested in these other two. 5, choose 2. And here, exactly the same thing. 2 R's, 2 A's, 1 L, and it doesn't matter which L it is out of those two, so we're not interested in that at all. All we're interested in is the other letters that we pick with it. 5, choose 1. Same again here, 5, choose 1, and here, 5, choose 0. So 5, choose 2 is 10, 5, choose 1 is 5, 5, choose 1 is 5, 5, choose 0 is 1. 10, add 5, add 5, add 1 is 21. Question 7a starts like a fairly straightforward probability question. We want the probability that they prefer swimming. So let's add these up. That's 135 over the total, because we're picking a student at random from everybody. So 135 over 400. We can simplify it, or maybe write it as a decimal. Let's see what we get. 27 over 80. Let's write it as 27 over 80 to keep it exact. The second part tells us to determine whether these two events are independent. So the events are: the student is male and the student prefers swimming. So to show that these two events are independent, we are going to find the probability of being a male, the probability of preferring swimming, and if when we multiply them we get the probability of being male and swimming, if we get that those two things are equal, let me just write that out to make it a little bit clearer. If independent, PS times PM is equal to PM intersection S. So that's what we're trying to prove if they are independent. P of S we've already worked out. Let's work out the P of M. So that is the number of males, so 31, add 57, so 88, add that to 90, so 180. Out of 400. We can simplify that as well. So 9 over 20. And now let's also work out the probability of being male and preferring swimming. So male swimming, that's that one there, 31 over 400. Now let's work out if P of S times P of M gives us that answer. P of S times by P of M equals 27 over 80 multiplied by 9 over 20. So 9 over 20 times 27 over 80. And we get 243 over 1,600. So they are not independent. It's not equal to 31 over 400. They are not independent. Okay, so all that means is that either males or females are slightly more likely or slightly less likely to prefer swimming in this sample. Okay, so it's not the same for both groups of people. Part B of this question seems to go along a slightly different tack. It doesn't seem to relate to the previous part as much. So, we're now talking about all the schools in this country, and 30% do not like any sports. We have 10 of the students chosen at random and a probability that at least 3 of them do not like any sports. To me, this sounds like a binomial distribution question. We have a fixed number of trials, Our success is not liking sport, and here is our probability of not liking sport. So this is distributed binomially with 10 as our number, n, and our probability is 30% or 0.3. Okay, so this is what we're looking at here, our binomial distribution. We want to find the probability that at least 3 of them do not like any sports. So that means the probability of 3, 4, 5, 6, 7, 8, 9 and 10 all added up. An easier way to find that is going to be 1 minus probability of x equals 0. Let's call this x. X equals 1 and x equals 2. So that's what we'll do. 1 minus, now p of x equals 0, this is what we're doing, n choose 0 times p to the power of 0. Our probability is 0.3, so 0.3 to the power of 0 and 0.7 to the power of 10 plus n choose 1. Now I shouldn't be writing n, I know what n is, it's actually 10, let's fix that. 10 choose 1 times 0.3 to the power of 1 times 0.7 to the power of 9 plus 10 choose 2, 0.3 squared times 0.7 to the power of 8. I'm going to work out these separately first, as long as they give me okay numbers. Maybe they won't actually. 0.7 to the power of 10 is probably going to give me something quite awkward. It does indeed. Okay, so let's work out each of these and then subtract from 1. So 10 choose 0 is 1, 0.3 to the 0 is 1. So we have 0.7 to the power of 10. I might just write them down at least to 3SF. 0.0282, but then I'm going to store them. Okay, plus 10 choose 1 times 0.3 to the power of 1 times 0.7 to the power of 9, which is 0.121. I'm going to store that in B. And then the last one, 10 choose 2 times 0.3 to the power of 2 times 0.7 to the power of 8. So 0.233, I'm going to store that in C. I'm now going to do 1 minus all of that. So P that x is greater than or equal to 3 is 1 minus recall A, add recall B, add recall C. So the probability is 0.617. The very last part of the paper is quite a common question to end the paper with, and it is turning a binomial distribution question, a binomial problem into a normal distribution and using a continuity correction. So now we're taking 90 students at random and we are finding the probability that fewer than 32 of them don't like sports. So our probability is the same, our probability is still 0.3 and our number is 90, and we somehow want to turn this into a normal distribution where we want mu and we want sigma, the standard deviation, squared. So to do that, we're going to look at our formula book, and our formula book tells us for the binomial distribution, mu is equal to n times p. So 90 times 0.3, which is 27. That's basically telling us that if we have 90 people, we would expect 27 of them not to like sport. Now let's work out our variance. Sigma squared is equal to np times 1 minus p. We just worked out np, it's 27. 1 minus p is 0.7. So 27 times 0.7. 27 times 0.7 is 18.9. So now I can replace those values here. And we've got 27 and 18.9. Watch out, this is the variance. When we use it in our normal distribution, we're going to want to square root it. So we are trying to find the probability that x is less than 32, fewer than 32. We're going to do a continuity correction here because our normal distribution is continuous. So that number 32 is almost like a class which goes from 31.5 to 32.5. We don't want to include 32, we want less than 32. So we are going to take the lower class boundary of 31.5. That's called a continuity correction. Let's now normalize this. So that would be p of z is less than 31.5. Subtract 27 divided by the square root of 18.9. So that is z is less than, we'll get our calculator and do 31.5 minus 27 divided by the square root 18.9. So 1.035. If we were to draw a little diagram of that, it looks something like this. Here's our 1.035, and we are looking for this area on the left hand side. So let's go to our tables. And look for 1.035. 1.035 is this one. This one, so we're doing 0.8485, add that 12, so 0.8497. So to three significant figures, that's 0.850 to 3SF. Job done.